Hi everyone, in my previous lecture we talked about the double pendulum. We obtained the equations of motion of the double pendulum using the Lagrangian approach, and then we simulated the nature of its solution and took a look at the chaos of the double pendulum. If you have not watched that video, then you should probably watch that video first, because today I'm going to restrict my attention to only small angle approximations. If we can create a setup where the double pendulum is restricted to small angles, what is the nature of its general solution? Well, as I will show you today, if we can restrict the motion of a double pendulum to very small angles only, then the nature of the solutions that we obtain are actually quite interesting. Here in the left hand side, the blue plot simply represents the angular displacements of the first mass, and the red plot represents the angular displacements of the second mass. Now, of course, you can see that the angular displacements of mass m1 and m2 are not SHM. But as it turns out, there are two sinusoidal frequencies hidden in the general solution. There are two simple harmonic oscillations of different frequencies hidden in the general solution of both mass m1 and m2 of a double pendulum. And today I'm going to extract those two simple harmonic oscillations that are hidden in the general solution, thereby demonstrating to you that the double pendulum is in fact a coupled oscillator for small angular approximations. It behaves as a coupled oscillator, two oscillating systems combined together. So therefore, I'm going to show to you how the double pendulum can ultimately execute SHM under certain kinds of given initial conditions, which is known as normal modes and normal frequencies. And to do all of this, I'm going to analytically solve the equations of motion. I'm going to obtain the normal frequencies and the normal modes of a double pendulum, and I'm going to demonstrate to you how two simple harmonic oscillations are hidden in the general solution of this double pendulum for small angle approximations. So if you have not watched my previous video, maybe you should take a look at that one first, because that is where I'm going to start from today. So let's start. Alright, so the setup of a double pendulum that I created was this. You have a point mass m1 and another point mass m2 connected to each other by, let's suppose, massless rods of lengths L1 and L2 respectively. And their coordinates are x1, y1 and x2, y2 respectively in the xy plane. But as far as angular displacements are concerned, we can think of their displacements as θ1 and θ2 respectively with respect to the vertical axis. Now, I have already obtained the Lagrangian for this kind of a setup in my previous video, so I'm not going to obtain that today. If you are interested in obtaining the Lagrangian for this setup, you can take a look at the previous video. I can do a brief revision for that. So what I did was I simply looked at the x1 and x2 in terms of θ1 and θ2 and y1 and y2 in terms of θ1 and θ2, which simply comes about from the geometry of the setup. And from there, to obtain the Lagrangian, I calculated the potential and the kinetic energy. The potential energy is kind of obvious. If I choose that the ceiling has zero potential reference, then the potential energy is nothing but this distance m1g y1 and this distance m2g y2. I substituted these transformation equations from 1, 2, 3, 4 into this, and I obtained the potential energy expression. Quite simple, right? The kinetic energy is just half m1 v1 square, the velocity of the first mass, and half m2 v2 square, which is the velocity of the second mass. The velocity of the first mass, if the mass is restricted to a plane, is just x1 dot square plus y1 dot square, and the velocity of the second mass, if the system is restricted to a plane, it's just x2 dot square plus y2 dot square. I used these transformation equations to substitute these quantities here to obtain the final expression for the kinetic energy, which I have already done in my previous video. And combining the kinetic and the potential energy, I obtained the Lagrangian. So this is just a brief recap. If you're interested in the problem, you should definitely take a look at the previous video where I've actually obtained the Lagrangian, which is of this particular expression. In today's video, I'm going to start from here. I'm going to use the Lagrangian to obtain the equations of motion for small angular approximations. So now that we have the Lagrangian, if I apply the small angular approximations, I need to consider situations where this particular quantity cos θ1 minus θ2, cos θ1 and cos θ2, they will approximate to certain quantities. So for example, for small angles, I can say that cos theta 1 is approximately equal to 1 minus theta 1 square upon 2. All right, and cos theta 2 is approximately equal to 1 minus theta 2 square upon 2. All right, and cos theta 1 minus theta 2 is approximately equal to 1 minus theta 1 minus theta 2 whole square upon 2. Since theta 1 and theta 2 are both small angles, therefore there are going to be 3 terms involved in this particular square of the sum. So I can actually approximate it to 1 to simplify my calculations. So for small angles, if I make these approximations saying that we have sufficiently small angles where these approximations are true, then the general expression for the Lagrangian will transform into the following, which is where I'm going to start my calculations for today. So you will have half m1 plus m2 L1 square theta 1 dot square. The first term will remain the same. Half m2 L2 square theta 2 dot square. Second term will remain the same. The third term will become m2 L1 L2 theta 1 dot theta 2 dot. Now cos theta 1 minus theta 2 I can choose as just 1. All right, and here you have m1 plus m2 g L1. So cos theta 1 can be written as 1 minus theta 1 square upon 2, right? So this can be written as minus half theta 1 square, right? And the second term can be written as similarly minus half m2 gl2 theta 2 square, and the constants will simply come out to be plus m1 plus m2 gl1 plus m2 gl2. So this is the Lagrangian of the double pendulum under small angle approximations. Now to obtain the equations of motion, what I'm going to do is I'm going to just plug in the values of the Lagrangian in the Euler-Lagrange equations. Now here there are 2 unknown variables, theta 1 and theta 2. So the equations of motion will be with respect to theta 1 as well as with respect to theta 2 separately. So on one hand, I'll apply the Euler-Lagrange equation with respect to theta 1, and on the other, I'll apply the Euler-Lagrange equation with respect to theta 2. So the nature of the Euler-Lagrange equation is d upon dt del L upon del theta 1 dot minus del L upon del theta 1 is equal to 0. And with respect to theta 2, you have d upon dt del L upon del theta 2 dot minus del L upon del theta 2 is equal to 0. So I need to obtain these terms first. So let me obtain these terms. So here I need to obtain what is del L upon del theta 1. So if you look at this expression for the Lagrangian, even though it looks lengthy and complicated, but it's ultimately the equations of motion are going to be much more simpler, because if I am differentiating with respect to theta 1 here, then how many terms are there that contain theta 1? This is one particular term that contains theta 1. That's it. So del L upon del theta 1 is simply nothing but minus m1 plus m2 g L1 theta 1. That's it, right? And the next term I'm interested in is del L upon del theta 1 dot. Now how many terms are there which have del theta 1 dot? So this is one term and this is another term. So we'll have 2 terms here. First is going to be m1 plus m2 L1 square theta 1 dot, and the second term is plus m2 L1 L2 theta 2 dot. That's it, right? So therefore the equation of motion, to write down the equation of motion, I'll have to now do the time derivative of the second expression. So d upon dt of del L upon del theta 1 dot is simply equal to m1 plus m2 L1 square theta 1 double dot plus m2 L1 L2 theta 2 double dot. Here the dot simply represents time derivative. A single dot means single time derivative, double dot means a second order time derivative. So if I plug all of this into the Euler-Lagrange equation, so in that kind of a situation, the Euler-Lagrange equation simply becomes m1 plus m2 L1 theta 1 double dot plus m2 L1 L2 theta 2 double dot minus m1 plus m2 gl1 theta 1 is equal to 0. So this is one of the equations of motion. with respect to theta 1. Now I can do the same thing for theta 2. So if I do the same for theta 2, then the first partial derivative I'm interested in is del L upon del theta 2. So here we have in terms of theta 2. So how many terms are there that contains theta 2? Just one term. Okay, so this becomes quite easy. So this is nothing but minus m2 gl2 theta 2. Similarly, the next partial derivative I'm interested in is del L upon del theta 2 dot. So how many theta 2 dot terms are there? You just have this term and this term, right? So you'll just get two terms here. The first term is m2 L2 square. So this is equal to m2 L2 square theta 2 dot, and then the next term is plus m2 L1 L2 m2 L1 L2 theta 1 dot. That's it. And the next is time derivative of del L upon del theta 2 dot, which is nothing but m2 L2 square theta 2 double dot plus m2 L1 L2 theta 1 double dot. If I plug all of this into the Euler-Lagrange equation here, then this takes the form of the equation m2 L2 square theta 2 double dot plus m2 L1 L2 theta 1 double dot minus plus. So here I think I missed a minus sign. So this is supposed to be plus, right? Here also, and here also it's supposed to be plus m2 g L2 theta 2 is equal to 0. So there you have these two equations of motion, which are second order differential equations of motion for a double pendulum under small angular approximation. Now I want to make this system a little bit much more simpler. And I want to do this because I'm only interested in obtaining the normal modes and the normal frequencies of this kind of a double pendulum. So I'm going to do a further approximation. I'm going to take a setup where the masses, the point masses are equal and the lengths of the rods are also equal. That let's suppose that the masses m1 and m2, the point masses of the double pendulum setup, are equal. And let's suppose the length of the rods are also equal. If we make this kind of an assumption, then automatically the first equation simply becomes 2m L square theta 1 double dot plus m L square theta 2 double dot plus 2m gl theta 1 is equal to 0 under these two approximations. And the second equation, this one, is simply going to become m L square theta 2 double dot plus m L square theta 1 double dot plus m gl theta 2 is equal to 0. And I can further simplify them into, let's suppose this is, if I divide this entire equation by, let's suppose 2ml square, this is going to become theta 1 double dot plus half theta 2 double dot, and this is going to become 2ml square. So g upon L theta 1 is equal to 0. And here, if I divide this entire equation by, let's suppose ml square, this is going to become theta 2 double dot plus theta 1 double dot plus g upon L theta 2 is equal to 0. See, now you end up getting much simpler looking equations. So let me write down these two equations finally. So finally, the equations of motion of the double pendulum are, the first equation is theta 1 double dot plus half theta 2 double dot plus g upon L theta 1 is equal to 0. And the second equation is theta 2 double dot plus theta 1 double dot plus g upon L theta 2 is equal to 0. These are the two second order ordinary differential equations corresponding to a double pendulum under small angle approximations. And as you can see, if you saw my previous video where we obtained the equations of motion for the general case scenario, compared to that, these equations look much simpler. In fact, in my previous video, we solved the general equations of motion computationally using the help of some kind of a computation software. But these equations right here in front of you, corresponding to the small angle approximations, can be solved analytically. And we're going to solve these second order differential equations of motion corresponding to the double pendulum analytically. And how can we do that? We can do that by writing these two simultaneous second order differential equations in compact matrix form. And in matrix form, this simply becomes 1 half 1 1 theta 1 double dot theta 2 double dot plus g upon L 0 0 theta 1 theta 2 is equal to 0. These two second order differential equations can be written in matrix form in this particular manner. Or quite simply put, this is a differential equation of the form, let's suppose m theta double dot plus k theta is equal to 0, where m is the matrix 1 1 half 1, k is the matrix g upon L 1 0 0 1, theta is simply theta 1 and theta 2. So theta 1 is the angular displacement of the first mass, theta 2 is the angular displacement of the second mass, and theta double dot is quite simply put theta 1 double dot and theta 2 double dot. So therefore, finally, I write down the two equations of motion corresponding to the double pendulum in this very compact form of a second order differential equation. Now, if you take a look at this differential equation, some of you may already be very familiar with differential equations of this form, because differential equations that look like this have sinusoidal solutions. But since in this compact matrix form we have two simultaneous differential equations of this form, we will have two distinct sinusoidal solutions which will come out as solutions when we solve this particular equation. So the solutions of these kind of differential equation are actually simple harmonic oscillations, or rather I must say a linear combination of simple harmonic oscillations. So the solutions of these kind of differential equations, theta, which corresponds to theta 1 theta 2, will actually turn out to be of this form. Let me write down first. So this is the real component of e to the power I omega 1 t plus, let's suppose here we have these components x1 2 and x2 2 e to the power I omega 2 t. So what is this? Because this is a second order differential equation, but in matrix form, which contains two individual differential equations that need to be solved simultaneously. So the solutions will be of the form e to the power I omega 1 t plus e to the power I omega 2 t, where omega 1 and omega 2 are what is known as normal frequencies. And here what x1, x2 they represent, they simply represent some kind of a constant which is multiplied to this particular expression. And since this may contain complex components, we will only take the real components here. Mathematically speaking, omega 1 and omega 2 are the eigenvalues, and this particular quantity and this particular quantity are the eigenvectors of the equation, the determinant equation k minus omega square m is equal to 0. The determinant equation that can be created by k minus omega square m is equal to 0, its solutions will give us the eigenvalues which will correspond to the simple harmonic solutions contained within the general solution I was talking about, and corresponding to them we will also have to obtain the eigenvectors. So therefore the next solution is to actually solve this particular determinant equation. So let's do that. So this is much easier actually. Just substitute whatever we have obtained here. So this is a determinant. So what is k? K is nothing but g upon L and g upon L and 0 and 0. What is minus omega square m? So this is minus omega square. This is minus omega square upon 2. This is minus omega square, and this is minus omega square and the determinant of this is equal to 0. So let us solve that. If we solve this equation, we will end up obtaining the eigenvalues and the eigenvectors associated with this compact matrix form of a second order differential equation, which will finally actually give us the solutions corresponding to theta 1 and theta 2. You will see how that happens. So let's solve this. Minus omega square with g upon L minus omega square minus, here you have minus omega square and minus omega square upon 2 is equal to 0. This can be simplified as g upon L minus omega square whole square minus, this can be written as omega square upon root 2 square is equal to 0, right? So root 2 whole square is just 2 and the minus minus cancels out here. So this is nothing but the expression for a square minus b square. So a square minus b square can be written as a plus b and a minus b. This is therefore g upon L minus omega square minus omega square upon root 2 and g upon L minus omega square plus omega square upon root 2 is equal to 0. So we will have two solutions corresponding to omega from here. So on one hand, we will have the equation g upon L is equal to omega square plus omega square upon root 2, and on the other hand, I'll have g upon L is equal to omega square minus omega square upon root 2. If I further simplify it, this simply becomes g upon L is equal to, in the denominator of root 2, you have root 2 plus 1 omega square, and here you have g upon L is equal to root 2 minus 1 upon root 2 omega square, which can be further simplified as omega square is equal to root 2 upon root 2 plus 1 g upon L, and omega square is equal to root 2 upon root 2 minus 1 g upon L. Let me write it in a better form here. So omega square is equal to root 2. Let's suppose we multiplied in numerator and denominator by root 2 minus 1. So and root 2 plus 1 and root 2 minus 1. What this will do, it'll change the form of this answer. So if I multiply here by root 2 and root 2 plus 1 in the numerator and again root 2 plus 1 in the numerator, then what I'll end up actually getting is that omega square is equal to, this is nothing but root 2 into root 2 is 2 minus root 2, and in the denominator I'll have root 2 plus 1 and root 2 minus 1 is just root 2 square, which is 2 minus 1 square, so minus 1, so g upon L. And similarly here you'll have omega square is equal to 2 plus root 2 divided by, this is nothing but 2 minus 1 g upon L, or omega square is equal to g upon L 2 minus root 2. This is one of the solutions, and the other solution is g upon L 2 plus root 2. So finally we have obtained the eigenvalues corresponding to this determinant equation we wrote before. Omega is equal to root over g upon L root over 2 minus root 2, and omega is equal to root over g upon L root over 2 plus root 2. So as we see that there are two distinct frequencies. Let's suppose the first is omega 1 and let's suppose the second is omega 2, which are hidden in the general solution of the equations of motion corresponding to the double pendulum for small angular approximations. But to obtain the general solution, first we also need to obtain the eigenvectors. So we have obtained the eigenvalues, which are actually the normal frequencies corresponding to this kind of system, but we also need to obtain the eigenvectors. So let's do that also. Okay, so first let's suppose we obtain the eigenvectors corresponding to omega 1. To obtain the eigenvector corresponding to omega 1, what we are going to do is we are going to write it in the matrix form of k minus omega square m. Alright, so k minus omega 1 square m Let's suppose one of the eigenvector is x. Okay, I write it as x here is equal to 0. Okay, so if I substitute this, all the expressions here, the equation will simply become g upon L minus omega 1 square, right? G upon L minus omega 1 square. And here we have minus omega 1 square upon 2. Here we have minus omega 1 square. And here we'll have g upon L minus omega 1 square, right? So this is the equation from which you can obtain the eigenvectors. And let's suppose the eigenvector corresponding to omega 1 is x1 1 x1 or rather x2 1 here, so which is basically equal to 0 0. So if I substitute what we obtained for omega 1, then this simply becomes g upon L minus g upon L 2 minus root 2, and this is minus half root over g upon L square. So this is nothing but g upon L 2 minus root 2. This is also equal to g upon L 2 minus root 2, minus sign here, and g upon L minus, so you'll have g upon L 2 minus root 2. Right, so let's just solve this. Let us try to obtain the eigenvectors corresponding to this, and to do that, let us simplify this. So what I'm going to do is I'm going to reduce the rows here somehow, but to do that, first let us take the g by L out of this. So if I take g by L out of this, this simply becomes 1 minus 2 plus root 2. Here you'll have minus 1 plus 1 upon root 2. Here you'll have minus 2 plus root 2, and here you'll have 1 minus 2 plus root 2. Further simplifying, I'll end up simply getting this is minus 1 plus root 2. This is minus 1 plus 1 upon root 2. This is minus 2 plus root 2. And this is minus 1 plus root 2. Now, if I want to obtain the eigenvector, what I can do is I can reduce this matrix that I have and make one of the rows 0. That will really simplify what I'm trying to do here. So what I'm going to do here is that I'm going to multiply root 2 with the first row, and then I'm going to add it to the second row, and I'm going to substitute it in the second row. If I do that, what happens? So if I multiply root 2 to the first row, which is this is the first row, right? And this is the second row. All right. So if I multiply root 2 to the first row, this simply becomes minus root 2 plus 2. And then if I add it to the second row, so the second row is nothing but minus 2 plus root 2, right? Similarly, if I multiply root 2 with this particular term here, so this is minus root 2 plus 1. And then here I have minus 1 plus root 2. And then if I substitute it in the second row here, okay, so if I substitute in the second row, the first row is still the same. The first row is still minus 1 plus root 2 and minus 1 plus 1 upon root 2. So what does this give us? This simply gives us a very simple solution for finding out the eigenvectors, because now this gets cancelled out, right? So one of the rows becomes 0, so which simplifies our problem. So minus 1 plus root 2 minus 1 plus 1 upon root 2, 0 0. And if I complete the set of equations here, so this simplifies our problem, because from here finally I can obtain a equation between x11 and x21, which is x11 minus 1 plus root 2 plus minus 1 plus 1 upon root 2 x21 is equal to 0. So from here what do we get? From here we simply get that x11 minus 1 plus root 2 is equal to 1 minus 1 upon root 2 x21. So finally we have x21 upon x11 is equal to minus 1 plus root 2 divided by 1 minus root 2, right? So if I divide it here, so this simply becomes root 2 minus 1. So this is nothing but root 2 minus 1 divided by root 2 minus 1 multiplied by root 2. So therefore this gets cancelled, and finally you end up getting x21 upon x11 is equal to root 2. Thus, if this is the eigenvector that I have corresponding to omega 1, so one of the solutions for the eigenvectors can be written as, if x11 is, let's suppose, 1, if x11 is 1, in that case x21 will come out to be root 2. So this is one of the eigenvectors corresponding to omega 1. Alright, very good. So now let us also obtain the eigenvector corresponding to omega 2. So if I am interested in finding out the eigenvector corresponding to omega 2, so I'm going to start from here, except that these will all be plus in sign because that is for omega 2. So with respect to omega 2, we are looking at the same k minus omega 2 square m and some x is equal to 0. Here, however, the components will be, let's suppose, x21 and x22, and omega 2 is 2 plus root 2, right? Root over g upon L, 2 plus root 2, right? So let's solve this. Okay, just take us a couple of minutes. So if I take GL out of it, this becomes 1 minus 2 minus root 2. This becomes minus half into 2. So this becomes minus 1 minus 1 upon root 2. This becomes minus 2 minus root 2, and this becomes 1 minus 2 minus root 2, which simply becomes x 2 is equal to 0, 0. So simplifying this simply becomes minus 1 minus root 2 minus 2 minus root 2 minus 1 minus 1 upon root 2 and minus 1 minus root 2. So here I'm again going to reduce the rows here. I'm going to multiply root 2 with the first row, and I'm going to subtract the second row, and I'm going to substitute that in the second row itself. That will simplify the problem that we have here. So if I multiply root 2 with the first row, so this is the first row here, okay, and this is the second row. If I do that, this simply becomes minus root 2 minus root 2, and then minus, this becomes minus plus, sorry, this becomes minus root 2 into root 2 becomes 2. This becomes plus 2 minus root 2, and minus root 2 minus 1 plus 1 plus root 2. This is substituting the second row. The first row is still the same, minus 1 minus root 2, minus 1 minus 1 upon root 2. So now this gets cancelled out, right? These terms gets cancelled out. Finally, we get a very simple looking equation, minus 1 minus root 2 minus 1 minus 1 upon root 2, 0, 0, and x21 x22 here is equal to 0, 0, right? This gives me the solution for x21 and x22. So this is minus 1 minus root 2 x21 minus 1 plus 1 upon root 2 x22 is equal to 0, or this simply becomes minus 1 minus root 2 x21 is equal to 1 plus 1 upon root 2 x22. So this becomes x22 upon x21 is quite simply put minus 1 plus root 2 divided by, so this simply becomes root 2 and root 2 plus 1, right? So this gets cancelled out and we are left with minus root 2. So finally we have x22 is equal to minus root 2 x21. So if this is the eigenvector corresponding to omega 2, in that case I can say that one of the eigenvectors, if x21 is equal to 1, then x22 is just minus root 2. That's it. So therefore, we have obtained not only the eigenvalues omega 1 and omega 2 corresponding to the compact matrix form of the second order differential equations corresponding to the double pendulum for small angular oscillations, we have also obtained the eigenvectors corresponding to omega 1 and the eigenvector corresponding to omega 2. That's it. We have solved the problem analytically. You see? we have the second order differential equations, two second order differential equations in compact form corresponding to the equations of motion of the second order, the double pendulum. We have solved it. We have obtained the eigenvalues and we have obtained the eigenvectors. Now we can write the solution in this particular manner. This is the manner in which we can actually write the solution in terms of omega 1, omega 2, and in terms of the eigenvectors that we have actually obtained. So let us do that and see what the solutions look like. The solution is for these differential equations corresponding to the double pendulum, written in this compact matrix form, can be written as theta is nothing but theta 1 and theta 2 can be written as the real components of the first eigenvector corresponding to omega 1 is 1 root 2, right? The first eigenvector is 1 root 2 corresponding to the omega 1. So this is I omega 1 t, where omega 1 is equal to root over g upon L root over 2 minus root 2, I think. And the second is the eigenvector corresponding to omega 2, which is 1 minus root 2 e to the power I omega 2t, where omega 2 is the eigenvalue, which is g upon L root over 2 plus root 2. That's it. We have obtained the general solution for theta 1 and theta 2, and I can write the solutions for theta 1 and theta 2 separately, but I can also take the real component of this exponential term, right? So what is this exponential term? Here we have e to the power I something, right? E to the power I, let's suppose ix. So e to the power ix is what? Cos x plus I sin x, right? So here you have the sort of the real part cos x and the imaginary part I sin x. So we are only interested in the real part here. So if I write down finally the solutions for both theta 1 and theta 2, let me write down these two first together. So theta 1 and theta 2 is simply nothing but, let's suppose there is going to be some kind of a constant here, okay? Let's suppose there's a constant C1 and constant C2. And whatever phase differences that exists, let's suppose that they are 0. So if I write this, this is simply equal to C1 1 root 2 cos of omega 1 t plus C2 1 minus root 2 cos of omega 2. So if I write the solutions separately, then I can say that theta 1 t is equal to C1 cos omega 1 t plus C2 cos omega 2 t, and theta 2 is nothing but root 2 C1 cos omega 1 t minus root 2 C2 cos omega 2 t. Finally, so these are the general solutions for both the masses of the double pendulum for small angular approximations. And look at the nature of the solution. It is quite interesting to see that the theta 1, which is the solution for the first mass, and the theta 2, which is a solution for the second mass, are in fact linear combinations of two sinusoidal waves. I mean, cos omega is nothing but sine omega plus pi by 2, right? So it's a sinusoidal variation. Cosine variation is sinusoidal variation. So here you have two sinusoidal variations, and their linear combinations are giving you the solutions for theta 1 and theta 2. I mean, if you took a look at the double pendulum, the general solution looked so complicated, right? But that general solution had these two frequencies hidden within them. One is the frequency cos omega 1t and the other is cos omega 2t in a particular linear combination. And the other is also omega 1t and omega 2t in a particular linear combination. So the general solution for both the particles in the double pendulum have hidden within them two simple harmonic oscillations, which is what's interesting about this setup. So there are two distinct simple harmonic oscillations that combine together in different proportions to create the general solution of a double pendulum. In fact, this brings me to the idea of the normal modes and normal frequencies, because I can extract these distinct frequencies out of this setup. So for example, what I'm going to do here is something very interesting. So how can I recombine theta 1 and theta 2 to extract the frequencies omega 1 and omega 2 out of it? So let's suppose that I choose this particular quantity root over theta 1 plus theta 2. If you look closely at this particular quantity, then this simply becomes root over C1 cos omega 1t plus root over C2 cos omega 2t plus root 2 C1 cos omega 1t minus root 2 C2 cos omega 2t. Here, these two terms gets cancelled out and you end up getting some kind of a variation of 2 root 2 C1, where C1 is a constant. Okay, right now I'm not interested in what's the value of these constants. We can obtain the constants using some initial conditions. But the general expression is just a pure sine wave. This is just a pure sine wave. Do you see here? This linear combination of the angles of theta 1 and theta 2 of mass m1 and m2 respectively is actually a sine wave. Similarly, if I also take another, let's suppose, linear combination of theta 1 and theta 2, let's suppose I take root 2 theta 1 minus theta 2, then this simply becomes root 2 c1 cos omega 1t plus root 2 c2 cos omega 2t minus root 2 c1 cos omega 1t minus plus root 2 c2 cos omega 2t. Here the first term and the third term cancels out and I end up getting 2 root 2 c2 cos omega 2t. So I end up getting sinusoidal variation here. Now what is interesting here to note down is that if you are studying normal modes and normal frequencies, then when you study coupled oscillators, here the double pendulum is in fact behaving as a coupled oscillator, then you will find out certain combinations of the coordinates that execute SHM. The coordinates of the individual particles themselves do not execute SHM, but some linear combination of the coordinates will execute SHM. So as you can see here, this quantity is executing SHM, this quantity is executing SHM, but the individual solutions are not executing SHM. Are you seeing that? So theta 1 is not executing any kind of a simple harmonic oscillation. Theta 2 is not executing some kind of a simple harmonic oscillations, but a linear combination of these terms, that is root 2 theta 1 plus theta 2 is executing SHM, some kind of a simple harmonic oscillation, and root 2 theta 1 minus theta 2 is executing some kind of a simple harmonic oscillation. Do you see how interesting this is? The particles or the motion corresponding to the particles m1 and m2 are not executing SHM, but the linear combination of their coordinates executes some kind of a sinusoidal variation. Therefore, these are actually known as normal coordinates. The coordinates of the particles are not executing SHM, but the linear combination of the coordinates are executing SHM. Therefore, these are known as normal coordinates. So what can we take from this? The general solution is a linear combination of simple harmonic oscillations. And in fact, we can take linear combinations of the general solution of both the particles, theta 1 and theta 2, that executes SHM. I can show it to you using a computational programming. Now, in my previous video, I discussed how to solve the equations of motion using some computation software. In today's video, we obtained the equations of motion and we solved the equations of motion analytically, right? It was quite simpler because we chose the small angle approximations. But in the previous video, we did not choose the small angle approximations. So the equations were actually quite complicated. And those second order differential equations required some kind of a computational help. If you know some kind of programming that and solve second order differential equations simultaneously, then that can numerically give you a solution to what you're looking for. And you can do that in various computational softwares like Mathematica, MATLAB. Maybe you can compute in Python. I took the help of Scilab. I created a program to solve the two second order differential equations of a double pendulum simultaneously for larger angles. Now, I'm not going to go into the details of the program. I'll put a link in the description. If you're interested in this program, I'll put a downloadable link somewhere. The program is such that I have the initial conditions here, right? Now, if I give some initial condition, let's suppose theta 1 for the first particle is 15 degrees and theta 2 for the second particle is, let's suppose, 0. Now, if I run this, I get what I was just talking about here, that these are 4 plots. The first plot, blue plot, represents the angular displacement of the first particle. The third red plot represents the angular displacement of the second particle. The second plot is basically the linear combination of root over theta 1 minus theta 2. And the second plot is the linear combination of root over theta 1 plus theta 2. So these are my results. So let me explain what the results are. Then we'll get a better understanding of what this is. The first graph simply is giving us an idea of how theta 1 is varying with respect to time. All right. And the second graph is giving us an idea of how theta 2 is varying with respect to time. The third one. And the second graph is simply, root 2 theta 1 minus theta 2. So root 2 theta 1 minus theta 2 is basically this, right? So as you can see, this is what we obtained from my computational program, a sinusoidal variation, or rather a cosine variation. And the last graph is quite simply put, this is root 2 theta 2 plus root 2 theta 1 plus theta 2, which is simply this. That's it. So this is simply some kind of a sinusoidal variation, right? So this is the sinusoidal variation of omega 2. Now omega 2 is root over g upon L, root over 2 plus root 2, right? And this is a sinusoidal variation of omega 1. So omega 1 is nothing but root over g upon L, root over 2 minus root 2. So as you can see, omega 1 is less than omega 2, right? So omega 1 is less than omega 2. It's a sinusoidal variation, but the frequency is less. And omega 2 is greater. It's a sinusoidal variation, but the frequency is more. So what is interesting is that these are the two distinct frequencies that are within the general solution of the double pendulum. So this is the general solution for the first mass of the double pendulum. This is the general solution for the second mass of the double pendulum, for of course small angle approximations. So what we have demonstrated here is that when you do a linear combination of these two, then you end up getting one of these solutions. And when you do the linear combinations of these two, then you get another solution. Are you seeing how interesting this is? The solution for the double pendulum for both the masses looks so random. It's like it's going up and down, right? But I mean, by looking at it, you might never be able to guess. But there are these two hidden frequencies inside them. A linear combination of these two frequencies can generate the solution for the first particle as well as the solution for the second particle. So that is all in this video, but if you have stuck with me till now, I want to reward you with a very interesting observation. Now this is the general solution for the first particle. This is the general solution for the second particle. They are not SHM, but by giving a very specific initial condition, I can make the double pendulum execute SHM. By giving a very specific initial condition, I can make the double pendulum execute SHM. These initial conditions and these configurations are known as normal modes. So I'm going to obtain the normal modes associated with the double pendulum in which the entire system is going to execute SHM. Now I can choose initial conditions such that these constants have a specific value. C2 is a constant, right? Let's suppose I choose some kind of an initial condition. I give it some kind of an initial condition for the system such that C2 comes out to be 0. Now, if I give that kind of an initial condition, in that kind of a situation, let's suppose at time t is equal to 0, what's going to happen? So if at time t is equal to 0, if I give angular displacement of the first particle theta 1 at time t is equal to 0, let's suppose I give it some kind of theta naught. Okay, theta naught I give. And let's suppose this theta naught is something. Let's suppose it's 15 degrees. All right. In that kind of a situation, what is going to be theta 2 at time t is equal to 0? Theta 2 at time t is equal to 0 is simply equal to root over 2 c1 cos omega 1t. Now, what is c1 cos omega 1t? This is nothing but root over 2 theta 1. So, theta 1 is nothing but at time t is equal to 0, theta naught. So, this is root over 2 theta naught. So, root 2 multiplied by 15 degrees. So, if I provide some kind of a small angles to the first particle, let's suppose 15 degrees, 10 degrees. And if I provide another displacement to the second particle, which is root 2 times the initial displacement of the first particle, in that case, I should get some kind of a sinusoidal variation of the entire double pendulum system. So coming back to my program, here what I'm going to do is I'm going to give 15 degrees to, let's suppose, the initial displacement of the first particle and 15 multiplied by root 2 to the initial displacement of the second particle. I'm going to run this program, but the general solution, I'm going to obtain the general solution for theta 1 and theta 2. Now remember, the general solution was quite complicated, right? The general solution of theta 1 and theta 2 are quite complicated, but what's going to happen if I obtain the general solution for these two specific initial condition cases? Let's run it. Yes. Now see, the solution is a simple harmonic oscillation. The blue line represents the angular displacement of the first particle. The red line represents the angular displacement of the second particle, and they are both varying sinusoidally. What does this represent? This represents a particular setup in which if the double pendulum is displaced by, let's suppose, theta naught for the first particle and theta naught into root 2 for the second particle, then the entire system executes simple harmonic oscillations. This is known as normal mode. So the normal mode of any coupled oscillator, and in fact the normal mode for this double pendulum which is behaving as a coupled oscillator, is that particular setup in which the entire configuration is executing SHM. In general, they don't execute SHM. In general, the general solutions for different initial conditions are not SHM. They are a linear combination of two SHMs. But for this specific initial condition, the entire setup is executing SHM. And which is this frequency? This frequency is omega 1, right? So the entire setup is executing SHM with respect to a frequency of omega 1. Now, can we make this setup execute an SHM corresponding to omega 2? Well, we can do that. First, notice here that the phase difference is 0. We can do the same for phase difference 180 degrees. So coming back to the normal modes, if we choose some initial conditions such that C1 is 0. Okay, if we choose some initial conditions such that C1 is 0, so theta 1, let me write it down again. So if I choose an initial condition such that C1 is equal to 0, then what is going to happen? Then at time t is equal to 0, if I provide some kind of a configuration or setup such that, let's suppose, theta 1 at time t is equal to 0 is equal to, let's suppose, theta naught, which is maybe 10 degrees, 15 degrees. I choose 15 degrees here, okay? In that kind of a situation, these are the two terms that will survive, right? So if these two terms survive, then in that kind of a situation, theta 2 at time t is equal to 0 will be equal to what? It will be equal to minus root 2 c2 cos omega 2t, which is nothing but minus root 2 theta 1 at time t is equal to 0, which is nothing but minus root 2 theta naught, or let's suppose minus root 2 into 15 degrees if this is what I choose. So if I arrange the configuration with a particular theta naught for the first particle and the negative of the square root multiplied by that particular angle for the second particle, then also I should execute an SHM for corresponding to omega 2. Now omega 1 and omega 2 are different, okay? Omega 1 had a different frequency, omega 2 had a different frequency. Let's run this for this particular initial conditions. So coming back to the program, if theta 1 is 15 degrees and theta 2 is minus 15 degrees, then also we should get a simple harmonic oscillation, but with a different frequency. So if I run this, there you have it. The blue line represents the simple harmonic oscillation of the first particle in a double pendulum. The red line represents the simple harmonic oscillations of the second particle. It means that if one of the particles is displaced by a particular angle and the other is also displaced by root 2 times that angle, but in the opposite direction, now the entire system will execute SHM in this particular manner. It means that particle 1 and particle 2 are executing SHM, but with 180 degree out of phase. So as you can see here, it's executing, both the particles are executing SHM with 180 degree out of phase, and the frequencies are different from the earlier frequency. So this is what's known as the second normal mode. So in the second normal mode, the system is executing SHM. That means all the particles are executing SHM, but with 180 degree out of phase. So as you see, this kind of a configuration in which the double pendulum actually executes SHM once in phase with a particular frequency, and the second time out of phase with a different frequency but executing SHM. These are known as normal modes. And the frequencies corresponding to these normal modes, that is omega 1 and omega 2, they are known as normal frequencies. And the general solution of the coupled oscillator is in fact a linear combination of these normal frequencies, which is what's interesting about coupled oscillators. See, double pendulum is in fact kind of a coupled oscillator, and it's a general behavior of coupled oscillators that the general solution of the coupled oscillators is a linear combination of the normal frequencies. The normal frequencies being those values which are hidden in the general solution, and you can find out what frequencies they are by giving specific initial conditions so that the entire system starts executing SHM in those particular frequencies. So that is all for today. I hope you enjoyed the video. I mean, it's interesting to see that the double pendulum is behaving as a coupled oscillator for small angular approximations. So a very quick revision. We started with the double pendulum, but with the Lagrangian. We obtained the Lagrangian in the previous video. Here we started with the Lagrangian. We applied the small angular approximations, right? And then we modified the Lagrangian. We applied them to the Euler-Lagrange equations with respect to theta 1 and theta 2. From here, we obtained the equations of motion. We wrote down the equations of motion in terms of a compact matrix form, which is actually solvable here analytically. And to do that, we have to obtain the eigenvalues and the eigenvectors of this particular determinant equation. We did that. We obtained the eigenvalues, which are nothing but the normal frequencies corresponding to the coupled oscillator, that is a double pendulum. And then we also obtained the eigenvectors solutions. This is one of the eigenvector corresponding to omega 1. This is another eigenvector corresponding to omega 2. And we finally wrote down the general solution of both theta 1 and theta 2, which are in fact linear combinations of two distinct simple harmonic oscillations. So that is all. As you can see, this general solution is a linear combination of these two, right? Which is quite interesting to see. That's it for today. Thank you very much.